Welcome to Numerical Methods for Scientists and Engineers with Pseudocodes. Video 4. Open Methods, Newton-Raphson and Modified Newton-Raphson Methods. The Newton-Raphson method is an iterative numerical technique used to find approximate solutions to equations of the form f(x = 0). It is one of the most powerful root-finding algorithms when the function behaves well and the initial guess is close to the true root. It's particularly useful for finding the roots, or zeros, of functions when a closed-form solution is difficult or impossible to obtain. The method requires an initial guess for the root, and then refines the estimates iteratively based on the function's behavior at the estimated point. Consider a nonlinear equation expressed as f(x = 0). To derive an iteration equation, we expand f(x) into a Taylor series about x0. This equation has an infinite number of zeros, so it is approximated as follows. Solving for x0 yields the following approximation formula. This is the first and hopefully an improved estimate for the root. If this estimate is sufficiently close to the root, the procedure is terminated, or the procedure is repeated as follows until the successive estimates become close enough to the root with reasonable accuracy. If the function for the second estimate x2 is sufficiently small, the estimation procedure is terminated. If not, a new estimate, x3, is computed, and, in the same way, it is tested for convergence. Introducing the superscript notation, the Newton-Raphson iteration equation can be expressed as follows, where xp denotes an estimate at the pth iteration step. To estimate the solution with d decimal place accuracy, the following convergence tests can be employed. The method is based on finding the tangent lines, followed by calculating the intercepts that eventually approach the true root. An initial guess is required to start the iteration process, which is often chosen based on an estimate of where the root of the function might be. We label the initial guess as x0, and then we find the point of vertical projection on the curve, which we will denote by p0. We then draw a tangent line to the curve at point p0. We extend the tangent line t1 to intersect the x-axis. We identify the adjacent and opposite sides of the resulting triangle. To find the x-intercept, we set the slope of the t1, the first derivative of f(x) at x0, to the tangent of the angle θ1. This gives an expression with x1 as the only unknown. Solving this for x1, we obtain the following first approximation. For the point x1, we find the vertical projection point p1 on the curve. Similarly, a tangent line drawn to fx at point p1 intersects the x-axis at x2. Likewise, the intercept of the tangent is determined from the slope of fx. That is, tangent θ2 is set to f'x1. This leads to an expression with x2 as the unknown. Solving this for the second estimate x2, we obtain the following approximation. Repeating this procedure successively yields a sequence of estimates x3, x4, and so on. The generalization yields the following iteration equation. The advantages of the Newton-Raphson method are: the method is simple, reliable, and easy to implement. Its convergence is quadratic when the initial guess is in close proximity to the root. Most divergence problems can be overcome by simply changing the initial guess. The disadvantages of the Newton-Raphson method are: The method requires an analytical evaluation of the first derivative. It may not be suitable for functions whose derivatives are difficult to obtain and/or require too many arithmetic operations. Convergence cannot be guaranteed for any given function or any initial guess. A division by zero problem may arise in case the derivative approaches zero. If a nonlinear equation has a root of multiplicity m greater than 1, it may diverge or converge very slowly with a linear convergence rate. Some functions, such as periodic functions, may exhibit unexpected behavior for a range of estimates. Consider the following nonlinear equation. Find its root for given initial guess and stopping criterion. The first derivative of the function is found as follows. We start with the initial guess x0 equals 1. We evaluate fx at x equals 1, which gives minus 3.7. On the other hand, the first derivative at x0 is obtained as 4. The ratio of fx0 to f'x0 is calculated to be minus 0.925. The first estimate can now be calculated, which yields 1.925. We repeat the process with the first estimate, x1 equals 1.925. fx at x1 is found as 20.80844. f'x at x1 is obtained as 67.65828. The ratio of fx1 to f'x1 becomes 0.307552. The second estimate is then calculated to be 1.617448. If we continue the iteration process in this manner, we find the converged result after 5 iterations. The sixth estimate is 1.384354, which satisfies the termination criterion. As p increases, the function evaluations and the ratio of fxp to f'xp approach 0. f'xp approaches 17.3636. The true root is an estimate obtained to 9 decimal places of accuracy. The sixth estimate is found as 1.384,354, which has an absolute error of 1.3 times 10 to the minus 8. The Newton-Raphson method fails when f'xp equals 0. Likewise, when fx has a multiple root, say in x equals alpha, the function as well as its first derivative for alpha becomes 0. Depending on fx, the iteration procedure may diverge or oscillate about the true value. Consider a continuous and differentiable function fx with at least one repeating root. We define a new function, u, as follows, where the functions fx and ux share the same root. Applying the Newton-Raphson method to function ux, we obtain the iteration equation in terms of u and u prime, or we may cast it in terms of the first and second derivatives of fx. However, if we know that fx has a root of multiplicity of m, we can speed up the method by replacing the iteration equation with the following. The modified Newton-Raphson method has the following advantages. The method is simple and easy to implement. The modified iteration equation is computationally effective and fast if the multiplicity is known in advance. Both schemes of the modified method, like Newton-Raphson, converge quadratically. The modified Newton-Raphson method has the following disadvantage. The modified Newton-Raphson iteration equation requires deriving and calculating explicit expressions for the first and second derivatives, besides f(x), which can be computationally expensive for complicated functions. That is all for now. See you next time with another topic. Bye.